Assalamualaikum dear viewers, hope you are doing well. I am Shoaib and Dayo, again here with another informative video related to the electrical engineering and the MATLAB simulation. Dear viewers, today we are going to perform the open circuit test of the transformer on the MATLAB software. This test is conducted to determine the iron losses or the core losses in a transformer. The primary side of the transformer, which is the LV winding, is energized from the AC supply, and the secondary winding of the transformer, which is the HV winding, is left open circuited. Normal rated voltage is applied to the primary winding of the transformer, which is the LV winding, and normal iron losses are established or produced in the core of the transformer. Since no load current is very small, which is the 2 to 10% of the rated current, so copper losses in this test are negligible compared to that of the iron losses. Hence, wattmeter, which is connected on the LV winding of the transformer, which is the primary winding, will gives the practically iron losses or the core losses which are same at the all loads. So without wasting time, let's do the simulation. So dear viewers, our main task is to conduct the open circuit test of the transformer on the MATLAB software. So before doing the simulation, let's discuss some few points of the open circuit test of the transformer. So this test is conducted to determine the iron losses or the core losses in a transformer. This is the circuit diagram of the open circuit test of the transformer. As you can see, the LV winding of the LV winding, which is the primary winding over here, is energized from the main supply, AC supply, and HV winding of the transformer is left open circuited. Okay, so the voltage is applied to the primary winding, which is the low voltage winding, and while the secondary winding is left open circuited. Normal rated voltage we are given to the primary winding, which is the LV winding of the supply, and normal iron losses are to be produced in the or occur in the core of the transformer. Since no load current is very small, because this no load is current is very small, which is the 2 to 10% of the rated current. So copper losses under the no load condition are negligible, and in the comparison to that of the iron losses. So hence this wattmeter, okay, which is connected on the LV winding of the transformer, which is the primary winding, so which will give us the practically iron losses which are same at all the loads. So this wattmeter will give us the practically iron losses. Okay, this ammeter would give us the no load current which is flowing in the LV winding of the transformer, which is the primary winding. The applied voltage which is given to the LV winding or the primary winding of the transformer read by this voltmeter, which is connected in parallel across the LV winding. So input power, the formula for calculating the power in the AC circuit is that VI cosine of Y. So here V1 is the applied voltage and I naught is the no load current, and cosine phi naught is the power factor. So how you can calculate the no load power factor? So no load power factor will be calculated with the help of this formula. Cosine phi naught is equal to W naught, okay, which is the iron losses, and divided by V1 over I naught. So let's do the simulation on the MATLAB software. So go to the Simulink model, take a blink model. Okay, now go to the power LIB. Okay, now drag the components. We need AC source. Okay, and we need the transformer. Okay, and also we need measurement block. Need voltage measurement. We need current measurement. Also we need ground. Also we need the power GUI block. Okay, now assemble the circuit as per the circuit diagram. Now this is a 3 winding transformer. Make it 2 winding. Okay. Now connect this ammeter in series with the primary winding of the transformer. Okay.
Now here this primary winding can be called as the LV winding. Okay. Now this is the voltmeter. Again, we need another voltmeter. Okay. Now we need the root mean square value block. Okay. Now also we need display. Okay. So here this is so this will give us the no load current, okay, which is I naught, and this is the simple I RMS. Okay. Now this voltmeter is connected in parallel with the primary winding, which is the low voltage winding in this case. Now this voltmeter will give us the primary voltage, which is the low voltage, will give us the reading. Now this will give us the primary voltage, normally called as E1. Okay. This is another voltmeter. This secondary winding, which is the HV winding over here. Okay. Now this should be left open circuited. If it is left open circuited, now we can connect the voltmeter in parallel across the this HV winding to just measure the secondary side voltage, which is HV voltage. So now again we need another display and RMS block. Okay. Now this would give us the secondary side voltage. Okay. This will give us the secondary voltage, which is the E2. According to this circuit diagram, now this ammeter will give us the no load current. Okay. This voltmeter will give us the V1 applied voltage to the primary winding of the transformer, and this will give us the E2 voltage, which is the secondary voltage. Now we have to measure the power factor cosine phi naught. Here in this case there is no block is available in the MATLAB, so design the power factor measurement block to measure the power factor on the low voltage winding of the transformer, which is the primary winding. So for the power factor measurement, we need the active and reactive power module. Okay. We need math operations, in which we need the block trigonometric, and we need this gain block. Okay, we need the divide block, and we need the product block. Okay. So now this will give us the active power, and also we need the multiplexer. Okay. So now assemble these blocks, and then we will connect according to the as per the diagram. Product and divide, and this is the gain block. Okay, now we need an RMS block for this. Okay. Another RMS block. So now this will give us the VRMS. Here this product block will give us the apparent power, okay, which is the VI, and give this input to the apparent power, and this is the VRMS. So connect this VRMS to the voltage block and connect this IRMS with the current block. Now again we need this to calculate the active power. We need again inputs of this voltage, input of the voltage to this, okay, and for the current is to connect with this ammeter block. This P will give us the active power and this will give us the reactive power. Now the power factor is the ratio of VI active power cosine of X over here like angle divided by apparent power VI. So this will give us the cosine X. Okay. Now make it a cosine of phi, signal type real. Okay. Now this gain block will give us the angle between the voltage and current. So for convert into the radian into the degree, 180 divided by pi is the formula. Now this will give us the conversion of radian value into the degree value. Okay. So apparent power is to be divided and active power output connected to this multiplication. We need another display. Now here this output from this divider block, which is the ratio of the active power or apparent power here, which this will give us the power factor. Now this block will give us the value of the power factor, which is the no load power factor. Okay, and now we need another display. So this display will give us the value of the power angle, which is the angle between the voltage and current. Okay. Now also we need to measure the active power. So wattmeter reading will give us the practically iron losses which are same at the all load. So now this active power can be given by this block, power block. So we need another display. So connect with this one. Okay, now this display will give us the reading of active power in watts. Okay, this voltmeter will give us the secondary side voltage. This voltmeter will give us the primary side voltage. This will give us the power factor. Okay, and also another definition of the power factor is that it is the ratio of the active power or apparent power is called the power factor. So if we are going to connect another display with the output of this apparent power, so this is the output of this apparent power. So now this will give us the apparent power. This display will give us the result of the power factor. Now change the parameters as per the circuit diagram. We are given the 220 volts AC supply, frequency is 50 Hertz. Now each RMS block make at 50 Hertz. Again this will be the 50 Hertz, 50 Hertz, and this will be the 50 Hertz. This will be the 50 Hertz. Okay. Now make it frequency of the power block 50 Hertz. Okay. change the parameters of the transformer. So here active apparent power is 50 e power 3. We are selecting 50 hertz frequency. We are given the 220 volts, which is the LV winding, and 1000 volt, which is the secondary winding voltage. Apply this. Okay. So now we have changed all the parameters as per the circuit diagram. So now our circuit is ready for the simulation. Now run the simulation. Observe the results. So now you can see this is the power factor, okay, which is the cosine phi naught no load power factor of the LV winding, which is the primary winding energized from this AC supply. This is the primary voltage, which is measured by this voltmeter, which is connected in parallel across the supply side. So this is giving us the 155.6. Secondary voltage is the 707. Okay, the power, which is active power. Now practically 32.99, which is almost 33 watts, is are practically the iron losses, okay, which are to be given by this wattmeter. Now these are the practically iron losses, so in the watts. Now this is the no load current, which is the very small amount of the current flowing from this transformer LV winding, which is the primary winding, which is a 0.3 almost ampere to 0.299, which is the almost 0.3 ampere. We can also verify this power factor with the ratio of this active power. Active power is here 32.99 and 46.66 is our apparent power. Use the calculator. Okay, now what power factor is the ratio of the true power, which is the active power or apparent power. So now where here the active power is 32.99, okay, divided by 46 point, this is the apparent power, which is the 46.66. So now divide by this 46.66. Now our power factor is the same one, 0.707. You can see power factor is given by this block 0.707. Okay, now this is the power angle, which is the angle between the voltage and current that giving us this power factor. Okay, we can find out the power which is given by this power block, which is the practically these are the iron losses. Okay, now this wattmeter reading practically give the iron losses, which are same at the whole load. Okay, now we can also calculate the power, which is the 32.99 with the help of this calculator. Now what is the formula for calculating the power? Vi cosine phi naught. Okay, now what is the Vi over here? You can see the 155.6 is the voltage. Okay, what is the current? 0 point, which is the I naught current, 2.299. okay, multiplied by what is the cosine phi naught over here? 0.707. So multiply 0.707. Now the power is the same one, 32.99, which is almost the 33 watt. Okay, this HV winding, which is the secondary winding of the transformer, is left open circuited. So now this can be left open circuited. Okay, now again run the simulation. Now again we are observing the same parameters because only we have connected the voltmeter across the HV winding, which is the secondary winding in the case of the open circuit test of the transformer. Now this only give us the secondary side voltage. Okay, you can see, which is the 707 RMS voltage of this 1000 volt. So dear viewers, this was the MATLAB simulation of the open circuit test of the transformer that we have conducted on the MATLAB software, in which we have uh, measured the core losses or the iron losses in the transformer in the open circuit test of the transformer. Okay, and LV winding of the transformer is energized from the AC supply, which is, and the wattmeter will give us the practically iron losses, which is same at all the load, and HV winding, which is a secondary winding over here, is left open circuited or kept open circuited. Now here this is the open circuited, but only we need to just measure the output voltage by connecting the voltmeter in parallel, so just to give the output voltage, which is the secondary voltage, which is the HV voltage of the transformer. So this was the simulation of the open circuit test of transformer.
Dear viewers, this was the experiment regarding the open circuit test of the transformer that we have done on the MATLAB software, in which we have observed the results of the iron losses which were measured by the wattmeter, which was connected on the LV winding, which was the primary winding of the transformer, and also we have observed the results of the no load current and the no load power factor. So I hope that you have enjoyed the today's experiment, and at the last, do subscribe my YouTube channel Shoaib for more informative video related to the electrical engineering area. Thank you.